Okay, properties of fluid. So we will have a look at, we will go briefly with three stages of matter: solid, liquid, and gas. We will define the mass density, specific weight, and the weight density. We understand the meaning of the pressure term. We already discussed that one. We will look into the terminology of the gauge pressure and the absolute pressure. And if we got time, we will have a discuss between the ideal and real fluid, bulk modulus, and the viscosity with the temperature. So the last three we will do later, but the others we will try to cover with the numerical question as well. Now, when we discuss the fluids, we said the fluids are both gases and liquid, because you can put the gas in any container, you can put the liquid in any container, and it will take the shape of the container, hence it's fluid. So they have continuous deformation. The deformation is continuous. But with the solids, it's different. The solid have a specific shape and specific size. Okay, now if we move to the next one. Now, when we talk about the molecules of the solid, they are closer to each other than that of a fluid. Hence, they cannot move. There is a lot of attractive force between one solid molecule and the other solid molecule. And because the force is massive, they try to retain their shape. This is not the case with the fluid, where the attractive force is smaller, hence they can move freely or they can slip on each other. The difference between the gas and the liquid is the gas molecules are a lot closer, but the gas molecules are a lot further. The molecules in our liquid fluid is a lot closer to each other. So the gas, we can compress the gas. We already discussed that one. And the gas can expand indefinitely. It can expand as much as possible. If you put a gas in a balloon, if you decrease the outer pressure, the balloon is going to expand and keep expanding and keep expanding. Liquid, on the other hand, is not compressible. Okay, now the reason is because there is a force of attraction between them, and there is an outer force. The force of attraction is a lot more than the outer force which is trying to compress them. So even if you release the outer force, the molecules of the liquid are not going to go far apart. They will try to stick together. Okay, then we have a formula for density. Density, this is our symbol rho, is known as mass or volume. The units are either kilogram, meter cube, or grams per centimeter cube. So it depends on what is given, gram per centimeter cube. Now, just to give you an idea about different density of different hydraulic fluid, so they are trade names. Different density. If you have a look at that one, the density of water, the rho for the water, the pure water is around 10,000. No, 1,000, not 10,000 kilogram per meter cube. So if you got meter cube of water, that will be 1,000 kilogram. Now, different densities, the oil usually have a density less than water, hence it floats on water. Okay, now the next one, let me just zoom it for you. Now we know that density of anything, a fluid, they will increase with the pressure, because when you compress, they are closer to each other, hence the density increase. But if you increase the temperature, the density will decrease. So now they are showing you a different mineral oils at different density. So this one is at 1,000 bar, and if you increase the temperature, you can see the temperature here is less than 50. You're going you're increasing the temperature, the density of that thing is decreasing. Yeah, you can work other way around. Yeah, you decrease the temperature, the density will increase. And you can see like at different pressure, they have different densities. Okay. Then we have a term called specific weight. Is represented by a symbol gamma, like that, specific weight. Specific weight is weight in newtons over volume. The unit for that one is Newton per meter cube. Now these are relationship between the density and the specific weight. So that's a relationship. We will have a look at that one. So density is equal to specific weight divided by G. Or in other words, if you want just a specific weight, move the G on this side. So the equation will become specific weight is equal to rho G. That is a specific weight. G is 9.81, acceleration due to gravity. And this is the density. Now, if you look at the density dimensions, it's kilogram per meter cube or grams per centimeter cube. Yep. Okay, the units. We have different densities. So density of water is 9.79, let's say. Yep. This is a density of water at 20 degrees centigrade and at 1013 millibar pressure with a value of G as 9.81. Yeah. So it's 1013 millibar absolute pressure and at 20 degrees centigrade. Yeah. Okay. And these all densities are recorded at these temperature and these pressure values. Now the next one. Then we have a term called specific volume. Specific volume is 1 over the density. The units of specific volumes are opposite of that or density. Density was kilogram per meter cube. The unit of specific volumes are meter cube per kilogram. Specific volume, SV, is the volume occupied by unit mass of a fluid. If I give you like 1 kilogram of a fluid, how much volume it's going to take. So specific volume is reciprocal of the density. Usually we apply to the gases. Units are here. Okay. The next one is specific gravity. Specific gravity, the symbol for the specific gravity is Sg. It's defined as the specific weight of the fluid divided by the specific weight of the water. Hence, is specific to the water. So specific gravity of the oil is the specific weight of the oil divided by the specific weight of the water. Because in the weight there is a G which is 9.81. So we can get rid of the G and we can have the formula specific gravity of the oil is density of the oil divided by the density of the water at standard STP, standard temperature and pressure. Specific gravity is a unit, is a ratio. So it's a dimensionless, unitless quantity. So dimensionless ratio. Temperature pressure in physics we take as 4 degrees centigrade. But in engineering, we take around 1500 or 15 degrees centigrade. In the SI unit, the density of the water is 1 gram per centimeter cube, which is equivalent to 1000 kilogram per meter cube. So dimension are the same, density here, so it will be a dimensionless quantity. So usually when you write down, you need to write down at what temperature and what pressure, the values for the specific gravity. Now let's do one numerical question. We got the air at 20 degree and at atmospheric pressure, the density of the air is 1.2 kilogram per meter cube. We need to find out the specific gravity. We need to also find out the ratio of specific gravity of water to the specific gravity of air. And why we need these values? What's the importance of these values? So here you are given a temperature of 20 degree centigrade. You are given the value of the density of the air, which is here 1.23. We are given the water density. Water density is 1000. So the density of the water is 1000. Specific gravity of the air is the density of the air divided by the density of the water. And we have this value, 1.2 times 10 to the minus 3. It doesn't have any units, so no units. Now the specific gravity of the water is 1. If you take a reciprocal of that one, there is a button in your calculator which has x to the power of minus 1. Yeah, and if you use that button, that takes a reciprocal of that number straight away. That will give you 813. What does that mean? It means the water is 813 times heavier than the air. So the significance of this ratio, it gives you the comparison in terms of density with respect to water, how heavy that thing is with respect to water, or how lighter this thing is with respect to water, because water we use as a standard. Now let's say we got another example where we are given the specific weight of oil mixture at ordinary pressure and temperature is 9.81 kilonewton, so times 10 to the 3. So remember the kilonewton, if we got kilonewton, that equal to 1000 newton. Yeah, so you can convert that one. The specific gravity of the mercury is given 13.56, which means it is 13 times, more than 13 times heavier than water. Compute the density of oil mixture and the specific weight and the density of the mercury. So we were given the specific weight of oil mixture, which is 9.81. Now where we got 9.81 from here, it's 9.81. Then we need to divide that by 1000 to get 9.81. Yep. The density of oil, if we need to find the density of the oil, is, we got 9.8 divided by the value of the G, which will give you the value. And we got two new units now. We can have milligram.